Hello, my name is Vishal.
And my name is Aditya, and our topic for video presentation is analog IC design in biomedical applications. Imagine it's 2 a.m. and a heart patient is sleeping peacefully at home. Everything looks normal, but suddenly the heart rhythm goes abnormal and goes back to normal in a few seconds. No hospital visit, no diagnosis, nothing. But this might be an early warning for a serious heart disease.
This is exactly why modern healthcare is changing. Earlier, doctors used to check patients only during hospital visits, but wearable patches help patients to live normally while their health is being constantly tracked. This helps for early prevention and treatment of diseases.
But this leads to a deeper question: how do we actually listen to the human body? Our body is producing electrical signals all the time. Our every muscle movement, every thought, every heartbeat produces tiny electrical activities. ECG from the heart, EEG from the brain, and EMG from the muscles. But the problem is these electrical signals are extremely tiny compared to our everyday signals.
And it gets worse. These signals get easily disturbed by even our body movement and even by nearby power lines. Now the real engineering challenge begins. How do we capture something so small, so fragile, accurately and safely?
The answer lies in analog IC design, especially the analog front end. It carefully amplifies, filters, and protects these delicate biological signal and converts them into meaningful and digital health information.
Now that we understood the importance of biomedical analog systems, let's briefly go through the history of biomedical devices.
In 1958, when two individuals named Rune Enquist and Åke Senning created the first ever implantable pacemaker. It was roughly around the size of a cricket ball and lasted only for a few hours or days before needing a recharge.
As the IC technology matured, engineers started focusing on instrumentation amplifiers. Analog designers perfected the common mode rejection ratio, which we'll discuss in upcoming slides, to extract these tiny signals from our body. 1980s saw the transition from bipolars to CMOS technology, which increased the battery life from months to years.
The integration revolution happened in 1990s to early 2000s. This era focused on shrinking the front end. Instead of having a board full of chips, the designers moved towards system on chip architecture. Analog IC design could no longer exist in a vacuum. The challenge was to place analog amplifiers right next to noisy digital microprocessors without any interference.
Today, analog IC design in biomedicine is pushing the limits of physics. Modern chips are often batteryless, powered by RF waves, ultrasound, or even body's own thermal gradient. Many innovations are happening in neural interfaces and wearable health devices.
This slide shows the overall process flow of a typical biosignal measurement system. The signal originates from the human body and is picked up using electrodes.
These signals are then captured by sensors and passed to the analog front end, where they are amplified and conditioned.
Next, the conditioned analog signal is converted into digital form using an ADC or analog to digital converter.
Finally, digital signal processing is applied and the data is either displayed, stored, or transmitted for further use.
Now let's take a look at what actually the analog front end does. Its job is simple but critical. It amplifies weak biological signals and filters unwanted noises and interference, mainly the noises from power lines. It conditions the signal so that the ADC can read it properly.
And one more important thing, patient safety. Biomedical circuits should ensure no harmful currents enter the human body.
So yeah, AFE is basically the translator between human body and electronics. So let's start with one of the most important fundamental building block of analog electronics, the operational amplifiers, or simply the op-amps. An op-amp is basically a very high gain voltage amplifier that amplifies the difference between two input voltages.
In biomedical electronics, signals with like CapCut, ECG, EEG, EMG are extremely weak. These signals can't be processed directly, so we use op-amps to amplify them while preserving their important information.
Here you can see a basic operational amplifier. The non-inverting terminal is marked with plus and an inverting terminal is marked with minus. The gain or the output voltage depends on the difference of the input voltages.
The resistors connected around the op-amp forms the feedback network. This feedback controls the gain and amplification of weak biological signals.
So in simple terms, op-amps help us take tiny signals and make them strong enough to analyze.
Now let's move to a more advanced and very important circuit in biomedical electronics. The instrumentation amplifier is specifically designed to accurately amplify very small biological differential signals.
The instrumentation amplifier helps extract the useful signals and rejecting unwanted noise. Here you can see the classic basic three op-amp instrumentation amplifier structure. The first stage consists of two amplifiers that provide high input impedance so the signal source is not disturbed.
The gain of this amplifier is controlled mainly by resistor named OR gain. By adjusting this resistor, we can precisely set how much the tiny biological signal should be amplified.
The final stage here means the third op-amp here acts as a difference op-amp. It subtracts the two input signals and removes common noises. This key feature of the instrumentation amplifier, we call it as high common mode rejection.
Because of its high accuracy, low noise, and precise gain control, instrumentation amplifiers are widely used in ECG, EEG, and neural signal recording systems.
In short, this circuit allows us to measure extremely small bias signals reliably and even in very noisy environments. CMRR measures the ability of an amplifier to reject signals that are common to both input terminals while amplifying only the desired differential signals.
Mathematically, CMRR is defined as 20 log 10 of the ratio of differential gain to the common mode gain. Here, AN represents how strongly the amplifier amplifies the difference between the two inputs, while ACM represents how much of the common signal leaks into the output.
In an ideal amplifier, the common mode gain would be zero, resulting in an infinite CMRR. However, in real circuits, mismatch and non-idealities limit the achievable CMRR. A higher CMRR means better immunity to noise sources such as power line interferences, electromagnetic coupling, and ground noise.
After amplification, the next important step in biomedical signal processing is filtering. Analog filters help us remove unwanted noise and keep only useful part of the signal.
In real biological signals, noise can come from many sources: body movement, electrical interferences. Filters can clean these signals by allowing only a specific frequency range to pass.
For example, ECG signals are typically filtered using a bandpass filter of frequency around 0.5 to 150 Hz. EEG signals often require low frequency filtering, and filters also help remove motion noise and power line interference.
There are three main types of filters used. First, the low pass filter, which allows only low level frequency signals and remove the high level frequency noises.
Second, the high pass filter, which removes very low frequency noise while keeping the useful higher frequency components.
And third is the band pass filters, which allows only a particular range of frequencies to pass through. This is especially used in biomedical systems where signals exist within a known frequency band.
So overall, filters play a crucial role in cleaning biological signals and ensuring accurate analysis and diagnosis.
After amplification and filtering, the biological signal is still in analog form. But most modern systems like microcontrollers and digital processors can only work with digital data. This is where the analog to digital converters or ADC comes essential.
The ADC converts the continuous analog signal into discrete digital values. In simple terms, it takes a smooth real-world signal and turns it into numbers that a computer can understand and process. For example, a 16-bit ADC has 2 power 16 levels.
This digital conversion allows microcontrollers and DSP systems to analyze the signal, perform computations, and extract useful medical information from it.
Once converted into digital form, this signal can also be stored, transmitted, and displayed. This makes long-term monitoring, remote healthcare, and accurate diagnosis possible.
So overall, the ADC acts as a bridge between the analog biological world and the digital processing world.
Even after amplification and filtering, one major challenge in biomedical circuits is noise, especially at low frequencies. It is called as flicker noise.
The flicker noise is also called as 1 over F noise. This noise dominates at low frequencies, which is exactly where many biological signals exist.
As a result, this low frequency noise can distort ECG and EEG signals, reducing accuracy and making proper diagnosis difficult.
To overcome this problem, we use a technique called chopper stabilization. Chopper stabilization is a technique used to reduce low frequency noise and improve signal accuracy.
First, the input signal is modulated to a higher frequency. At higher frequencies, flicker noise becomes very small, so the signal can be amplified more cleanly.
Next, the amplifier boosts the signal in this high frequency region where the noise is minimal. Finally, the signal is demodulated back to its original baseband frequency, but now with much lower noise.
So overall, chopper stabilization improves signal clarity, reduces low frequency noise, and is widely used in precision biomedical amplifiers.
Here we can see the overall process of a chopper stabilized amplifier where the input signal is transferred to a modulator where offset and 1 by 1 over F noises are removed. Then it again amplifies the signal and demodulator shifts the signal back. Then low pass filter removes the lipper and we get a clean output. The biomedical devices can majorly be divided into four categories, that is, medical imaging technologies, physiological signal monitoring, sensors and transducers, and therapeutic and assistive devices.
Now let's look into the constraints involved in designing of chip in these devices.
Modern techniques such as ultrasound, MRI, and X-rays come under medical imaging technologies.
One of the key factors in medical imaging is resolution, which determines how clearly small structures inside the body can be seen. High resolution imaging helps doctors detect tumors, internal injuries, or abnormalities at an early stage.
Another important factor is safety. Medical imaging systems are designed to minimize harm to the patient. For example, ultrasound uses non-ionizing waves, and modern imaging systems carefully control radiation exposure to ensure patient protection.
Next comes data management. Imaging systems generate a large amount of data, which must be processed, stored, and transmitted efficiently.
Now let's take a look at sensors and transducers. These devices detect physiological signals from the human body and convert them into electrical signals for processing. Other thing.
The system shown here records important bodily functions like heart activity, respiration, and blood pressure. Another key factor is sensitivity and selectivity. The sensor must detect very small signals while responding only to the desired physiological parameter.
We also consider signal to noise ratio, which ensures the signal is clear compared to noise and which affects long-term accuracy and stability. The techniques shown here, such as EEG, ECG, and EMG, come under physiological signal monitoring. One major challenge in monitoring is motion artifacts. When the patient moves, unwanted disturbances can affect the signal quality. Half of the focus here.
Another important factor is the skin electrode interface. Proper contact between the electrode and skin is necessary to capture accurate and stable signals.
We also deal with non-invasive sensing, where signals are measured without entering the body, making the process safe and comfortable for patients.
Finally, modern biomedical systems use real-time processing to instantly analyze signals, enabling continuous monitoring and quick medical response.
One important design factor is power consumption, especially for implantable devices like pacemakers, which must operate reliably for many years on a small battery.
Next is fail-safe design. Since these devices directly affect human life, they must work reliably under all conditions and handle faults safely.
We also consider
Jacob.
latency and response time because therapeutic devices must react quickly to changes in patient's condition.
Finally, size and form factor are critical, especially for wearable and implantable devices, to ensure comfort and long-term usability.
Now let's deep dive into analog IC design in neural recording.
Neural recording is a fundamental technique used to observe activity in the nervous system. It provides a window into how the brain and nerves function during sensing, movement, and cognition.
So the first question we should ask is, what exactly are we measuring in neural recording? Here we are interested in extracellular action potentials, which are electrical signals generated when neurons fire.
These signals are extremely small in amplitude, typically in the range of 50 to 500 microvolts peak to peak. Because the signals are so weak, even small disturbances can significantly affect the measurement.
That brings us to the main question, noise. Thermal noise and low frequency 1 over F noise act as the enemy and must be kept well below the signal level to reliably detect neural activity.
To achieve this, the system is designed with a target input referred noise of less than 5 microvolts, which ensures that the recorded signal is not buried in noises.
Another critical constant is power consumption. Since the recording electronics operate very close to brain tissues, excessive power can lead to heating.
Even a 1 degree rise in temperature can cause brain tissue damage. So the entire system must operate at ultra low power while still maintaining high signal quality.
Now that we know what signals we are measuring, let's look at the overall system architecture used for neural recording. This slide shows the signal flow starting from the electrode and ending at the digital output.
The first block is the electrode, which acts as the interface between the brain tissue and the electronics. Materials like gold, platinum, or peyote are commonly used because they are biocompatible and provide stable signal coupling.
Next comes the low noise amplifier or LNA, which is the most critical block in system. Since neural signals are extremely small, the LNA amplifies them while setting the noise floor of the entire recording chain.
After initial amplification, the signal passes through a programmable gain amplifier or PGA. The PGA allows us to adjust the gain, typically between 40 to 60 decibels, so that the signal fully utilizes the ADC input range.
The amplified signal then goes through a bandpass filter. This filter removes unwanted DC offsets at low frequencies and suppresses high frequency noises.
Finally, the ADC or analog to digital converter converts the conditioned analog signal into digital bits. These digital signals can then be stored, processed, or transmitted for further neural analysis.
In the input stage, we used capacitively coupled instrumentation amplifier, but the main question is why capacitive coupling? The reason is that electrodes introduce large DC offsets, typically around 100 millivolts, due to electrochemical reactions at the electrode tissue interface.
Compared to neural signals, which are only a few microvolts, this DC offset is extremely large. If it is not removed, it can easily saturate the amplifier and hide the actual neural activity.
Capacitive coupling acts as a DC blocking mechanism. It allows the AC neural signals to pass through while blocking the unwanted DC component.
The instrumentation amplifier configuration is chosen because it provides high input impedance and excellent common mode noise rejection, both of which are critical for low amplitude neural signals.
So far, we have talked about how neural signals are acquired and processed. The next major challenge is how to get data out of the implant safely. This is what we mean by cutting the cord.
The main constraint here is biological. If wires pass through the skin, they significantly increase the risk of infection. So any long-term neural implant must be fully wireless.
However, making the implant wireless introduces another problem, that is power consumption. A conventional active wireless transmitter consumes a lot of power, which is not suitable for implanted systems.
To solve this, the system uses backscattering, also known as load modulation, for data transmission. Instead of actively transmitting, the implant simply changes the load on its antenna coil.
By shortening or opening the antenna coil, the implant modulates the signal sent by an external reader. This allows data to be transmitted without generating a new RF signal.
As a result, the power cost is near zero, making backscattering ideal for low power implantable neural devices.
The data shown here in this slide is compiled from well-known research papers published over the last 2 decades. Each column represents a representative front-end design from the literature rather than results from our own implementation.
Specifically, these works span from Harrison, Yazikuyoglu, Vatana Panich, with the final column showing a modern design target based on current research trends.
Looking at the techniques used, early papers relied on basic CCIE architectures, while later works introduced chopper stabilization and current reuse to improve noise power efficiency.
Most recent research is now moving towards digital assistance and AI-based calibration, which helps compensate for analog non-idealities at ultra-low power. Another clear outcome from the literature is process scaling. The technology node has reduced from 1.5 micrometer to deep submicron CMOS, enabling operation at much lower supply voltages.
This reduction in supply voltage from 5 volts to below 1 volt is critical for implantable systems where power and heating are tightly constrained. Interestingly, the input referred noise reported across papers remain in the few microvolt range. This indicates the neural signals limit are set more by biological constraints than by technology alone.
However, the power per channel reported in the literature shows a dramatic reduction from tens of microwatts to sub-microwatt levels, enabling large channel count systems. The noise efficiency factor or NEF is widely used in these papers to compare designs fairly. Lower NEF values reported in later work show better noise power trade-offs.
Overall, this literature survey highlights how research has steadily pushed neural frontend towards lower power, higher efficiency, and great scalability. We would like to specially thank Professor Gajendranath sir for guiding us through this topic.
We thank Shubhadeep sir for organizing this course beautifully.
And all other faculty members who made us understand all these complex topics so easily.